In this video, I will be, um, perhaps maybe in just one video, hopefully, I'll be showing you my grade 12 physics fourth quarter reviewer. So, um, yeah, basically, this is the formula sheet that I've used um, for the quarter exam. So as you can see, um, part of what we have here in the list, we have Ohm's law. Sorry, is my Apple Pencil working? Okay, so we basically have Ohm's law, thermal expansion, calorimetry, frequency period and waves, mirror equations, index of refraction, Snell's law problem, um, among other things. I think that's it. Um, so yes, we'll be using these formulas throughout this reviewer. In Ohm's law, let me start discussing the formulas. Starting with Ohm's law. Um, so basically, we have series circuits and parallel circuits. Each of them has three kinds of formulas, but essentially, uh, among these circuits, we have V, I, and R. So what's V? V is a voltage, I is current, and R is resistance. Voltage, the unit is in volts, or basically just small v. For current, I believe that is amps, in amps. And for resistance, it's in ohms. So, for series circuit, it is recognized that the current is constant. Therefore, current total is equal to current 1, current 2, and current 3. Assuming that you only have 3 currents in a certain scenario. But it could extend to I4, I5. It depends. But basically, for series, current is constant. For voltage, if you want to find the total voltage, you have to find the sum of all voltages. That also goes the same for resistance. Resistance 1 plus resistance 2 plus resistance 3, etc. For parallel circuit, what's constant here is the voltage. So voltage 1 is equal to V1 equal to V2 equal to V3. And for the current, in order to find the total current, you find the sum of everything. That also goes the same for the resistance. However, as you can see here, we have fractions instead of whole numbers, unlike series. For parallel circuits, the equation or the formula for total resistance, it's basically like this, written as this. So 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So this is one of the most common mistakes in calculating for the total resistance in parallel circuits. You forget that there's a fraction. So yeah. And yes, Ohm's law, essentially it's basically V is equal to IR. You can manipulate that equation when you look for voltage. V is equal to I. Sorry. Yeah. If you're looking for voltage, then it's basically the multiplication, or basically multiply I and R, the current and the resistance. If you're looking for current, given that you have voltage and resistance, the equation is written that way. If you're looking for resistance, resistance is voltage over current. Okay. But also another thing that you can mention from this equation, because they're being multiplied with each other, to each other, you can say that current has an indirect, or basically an inverse relationship with resistance. So if there's higher current, there's lower resistance. At the same time, if there is low current, then there is high resistance. How about the relationship between, let's say, if you're looking for current, we have V over R. Well, if it's a fraction, then it is certain that voltage, an increase in voltage is equal to an increase in resistance. Another way around. If you're looking for resistance, an increase in voltage, I believe it's also equal to an increase in current. Okay, so that's it. Let's move to thermal expansion. I hope I still remember these equations. Maybe I could start remembering them again once we actually go to the actual worksheet. But for now, yeah, just find a way to memorize these formulas. I think LF stands for latent heat of fusion. I'm not sure. We'll get to that soon. A, linear coefficient. Okay. Linear coefficient of steel is 12 times 10 raised to negative 6. The unit is over degrees Celsius for some reason. There is a reason for that, definitely. I just don't remember it too right now. And at the same time, it's also the linear coefficient value of concrete. For aluminum, it's 23. And it's the same thing, the rest. For steel, it's just 12. Aluminum, 23. That's one way to memorize it. Let's go to calorimetry. So yes, I think I remember this clearly. Clearly, it's one of my favorite formulas. Q is equal to MCAT. What's going on? Okay. So Q. Do I still remember this? Rick. For anyways, we'll get to that too later. But sure, M is mass, C is specific heat, and delta T is the change in temperature. What is the change in temperature? That's temperature high minus temperature low. Before, my teacher used to say that it was supposed to be TF minus TI, but it doesn't work in all scenarios. So what's a safer approach to what delta T is that it's supposed to be equal to T high minus T low. How about Q? I think Q means energy. So Q gain is equal to Q loss. And yeah, Q2 is MLF, Q4 MLV. This is associated. These equations could better be understood in a graph. Let me try making one right now. So this is temperature. I don't know what this is, but basically, this is LF, latent heat of fusion. This one is latent heat of vaporization. Melting point, we'll get to that too later, but basically the drawing is something similar to this. Let's assume that the substance or the substance that we have is water. The melting or freezing point of water is 0 degrees Celsius. The vaporization point or boiling point perhaps is equal to 100 degrees Celsius. More on that later. But there are certain values that you'd want to know Um, for the latent heat of fusion of water, it's 80 calories per gram. For the latent heat of vaporization of the same substance, that is water, it is equal to 540 calories per gram. Per grams. Or per gram. I'm not sure. What's the specific heat of water? It's 1 calorie per grams Celsius. For ice, it's 0 0.5, and for vapor, you can already say that it's also 0 0.5, but to be more specific, it's actually 0.48. Okay, we'll be using all of these formulas later in one single problem. Um, for frequency, period, and waves, frequency is 1 over t, basically the number of cycles over a period of time. And you can manipulate this equation into this. T is equal to 1 over f. And we have velocity right here. Is it velocity? I'm not sure. Can't believe I'm not sure. But this is lambda. Lambda times f. Waves times frequency. Okay. T is the interval of time between events. Okay, mirror equation. Uh, I should have written what di and do meant, like in a legend kind of system. More on that later too. But I think M means magnification. That I'm sure. The rest I'm not. Index of refraction, or Snell's law problem. With this formula, N is equal to C over V. Basically, N is refractive index. C is the speed of light, which is a constant. It's always going to be 3 times 10 raised to 8 meters per second. And V is the velocity of light in a medium. So if N is greater than 1, the speed of light slows down. If N is equal to 1, the speed of light is the same. Same with what? I'm not sure either. Anyways, if N is less than 1, then the speed of light is faster. And yes, the refractive index of air is supposed to be N is equal to 1. And another formula, I guess this is on Snell's law problem. N1 sine theta 1 is equal to N2 sine theta 2. Okay, so far we've gone through each formula, although I could have done better in describing each one. Definitely we would arrive to that point later on in this video or in future videos, probably part 2 or part 3. They would be explained better soon. Okay. So this is, we'll head over to Ohm's law first, series circuit. So again, like what I said earlier, in a series circuit, current is constant, described by this equation. Voltage, current, resistance. For the second detail and third detail, to find the total voltage and total resistance respectively, you need to find the sum. Sorry. Everything good? Okay. Actually, I did make a video about this in some time ago, a few months ago. So I won't be going through it anymore. But yes, this is what I did. Okay, so to reiterate again, um, in parallel circuit, in a parallel circuit, the voltage is constant, not the current. And for current and resistance, respectively, in order to find their values, actually, for a while, um, what I have here in number 3 is actually wrong. There's supposed to be a 1 over. Then we put the RT. So, again, like what I said earlier, it's pretty easy to make a mistake in parallel circuits resistance formula or equation, whatever you call it, um, because of the 1 over. But if you're very familiar with it, it wouldn't be an issue to memorize correctly. So, that's it. With these, it shouldn't be hard to um, solve these kinds of problems. Again, I'm not answering them right now because I've already answered them in the previous videos. Just type it up. Ohm's law, TM97. Okay, worksheet 4.3, combination circuit. So basically, we are combining series and parallel circuits in one scenario, like what you're seeing right now over here. So yeah, a video was already also made on this one, I believe. And yeah, this is just a retake of what I answered earlier. Okay. So let's go to thermal expansion. I think there was another video that was made um for related to this topic too. Ah, I mean, shoot, what's the point of making this video anyways if I keep saying that previous videos were already made on this. Well, yes. Like what I said earlier, these are fixed values on linear coefficients of certain things such as steel, concrete, gasoline, aluminum. So let's try number 1. Let's see how I was able to solve it. So we're given LO and LF. Sorry, LO is 30 meters. LF is 3.125. Okay, I think I'm starting to get it. You can call this LO or LI, but there's a reason why I placed LO instead. But basically, these two things, what do they mean? The topic is about thermal expansion. So basically, the main concept behind this idea is basically if temperature rises in a significant level, there is a tendency for example, a bridge. That's the reason why there are bridge gaps in between. Uh, it's actually because of thermal expansion. Um, if the concrete heats reaches basically a certain point where it starts to expand, um, yeah, basically when temperature rises significantly, um, certain solids can expand. Sorry. But yeah, that's basically it. Um, Initial length of a certain object is 30 meters, and the final length is 3.125. What increased? Um, this is actually legit. Anyways, I'm just surprised that it's not 30.125. Doesn't seem believable. Anyways, I think this is just theoretical, but I am certain that the answer is correct as well as the solution. This is just a fictional scenario. What we're dealing with is a fictional scenario. Initial temperature is 24 degrees Celsius, and the final temperature is 35. We're looking for the linear coefficient. I believe this is one way to trace an object. If we know that it's not known, we can trace it by finding the linear coefficient. Usually it matches. A linear coefficient value matches with a certain type of material, if I remember correctly in class. We use this formula. Uh, Change in length is equal to linear coefficient times initial length times the change in temperature. We manipulate the equation such that we're supposed to look for the change in length, because everything else we already have them, so we have to look for the change in length. Why? Because in the next formula, uh, let me think. Okay. Um, Actually, this formula was supposed to be used later, but in the meantime, we did use LF is equal to LO plus change in L. So yeah, that's a formula written earlier. Let me show you. There you go. It's this one. So length final is equal to length initial plus the change in length. Okay. Um, so after manipulating the equation, we have found the change in length, that is 0.125 meters. Looking for A, we manipulate this equation into this, and we fill in the values. The answer for the linear coefficient is this, 3.78 times 10 raised to negative 4 over degrees Celsius. So what is the linear expansion coefficient in the first place? This is basically the increase in length per unit length when the temperature is raised by 1 degree Celsius. More important formulas to know. Uh, Change in L, this is what we used. Um, Actually, these are the two formulas that were used in question 1. This one is this. That one is that. Okay, let's go to number 2. So we have a we have an initial length of 50 meters. The final length is not known. However, we have the temperatures initial and final. So basically, we can observe that it became colder from 30 degrees Celsius to 20. Um, but then it is implied that, well, basically in this question, the material the material that is being described is steel. So even though the question will not mention about the linear coefficient value of steel, it is already implied. So you just have to memorize the value. And from there, so looking for LF, we have to look for the change in length first through this formula. Uh, we can find the change in length without looking for LF first. So with this formula, linear coefficient is placed there, initial length over there, change in temperature. Um, I'm not sure why this is not high minus low, but it was still correct anyways. I don't know. Maybe, uh, don't get me wrong. It is still correct to say that change in temperature is T high minus T low. This is definitely correct in all situations. However, based on my experience with my teacher, um, this is also a good formula. However, it doesn't work in all kinds of questions. So just to be safe, I wouldn't use this, even if I used it here. Okay, so what we have for change in L is this value. Using the LF is equal to LO plus change in L, the answer is 49.994 meters. So as you can see, from 50 to 49.9, the change in size, it didn't expand. It did the opposite of expansion because the temperature was lowered. Okay. So yeah, this was the question for number 2. What was the length of the steel rod at 20 degrees Celsius when it was observed to be 50 meters in length at 30 degrees Celsius? Okay, calorimetry. This is gonna be fun, I guess. Okay. So Q is equal to MCAT. I've already mentioned these formulas earlier. By the way, for C, that is specific heat, I also mentioned that earlier, but just to add to that information. The specific heat of steel is 0.11 calories over grams times Celsius. The specific heat of a human is 0.83. Okay. This is the actual list. And yeah, let's try solving number 1. I already answered it. The answer is already in the page above before this, but let's try answering it again. So calculate the energy. Energy is missing. In calories for 15 pretzels if they raise the temperature of 150 grams of water in a calorimeter by 45 degrees Celsius. So what we're talking about is water. So how do we know the C value? So C, specific heat of water, we know that it's 1. What's the unit again? Calories over grams times degrees Celsius, I believe. I believe 45.3 is already the delta T. Is it? Yes, that is correct. So Q is equal to mass is 150 grams. Specific heat is 1 cal over G times degrees Celsius. And the change in temperature is 45.3 degrees Celsius. 150 times 45.3, what is it? It's this one, 6,795. Okay, how about number 2? So 500 grams of water absorbs 2,000 calories of heat. Definitely in the unit calories, we know that this is energy. That's the energy value. What is the temperature change experienced by the water? We know that we're talking about water. So C of H2O. What's the specific heat? It's still water. It's still in liquid form. If it were ice, then it's going to be 0.5. If it were vapor, it would be 0.48. But it's in liquid form, so it's 1. So Q is equal to MCAT. We're looking for the change in temperature. So you manipulate the equation like that, and then calorie mass is 500 grams, and then specific heat is 1 cal over. So what is the answer? 2000 divided by 500, that's 4. And what's the unit for temperature? Degrees Celsius. Let's see if the answer is the same. There you go. 4 degrees Celsius. Okay. How about number 3? 500, we have 550 calories of energy. Temperature of water is increased by 37.6 degrees Celsius. If we have this preposition by, definitely the following value is the change in temperature, or delta T. What is the mass of the water? We don't know yet. But we're talking about water, so what is the specific heat? It is implied that it's 1 cal over G times degrees Celsius. C is 1. Change in temperature is 37.6 degrees Celsius. 550 over 37.6 is what? 14.62766. Okay, number 4. We have 175 grams of water heated from. So, like what I said earlier, if we see by, definitely that's delta T. But if it's a different preposition, it may indicate a different idea or meaning. Like this. Like what we have here, it says from 20 degrees Celsius. So obviously, it could be said that this is the initial temperature. Maybe if it says 2, basically implying the idea that it is the final temperature, then it is the final temperature, or TF. But it's TI in this scenario. 375 calories of energy are produced. So we have the capital Q. We need to look for the final temperature of water. We're still talking about water, so the specific heat is still 1. So Q is equal to MCAT. We can rewrite the formula like this. Just for this scenario, it is correct to express delta T, or the change in temperature, as TF minus TI, instead of temperature high minus temperature low. So it's gonna be a hassle if we still apply distributive property. Let's just place in the values now and see what happens. 175 grams times the specific heat, 1 cal over like that. then TF minus TI. Either way, we're still gonna apply distributive property. We cannot escape the hassle. But we do know what TI is, right? It's 22. Why did I place it earlier? Hmm. One 175 times 22. Three 850. Okay. Makes better sense. If we move the degree Celsius unit to the other side, it would look like this. And let me just get my calculator real quick. Okay. So basically 4225 divided by 175 is dang, this is the slowest calculator. 24.1429, and then degrees Celsius. Do we have the same answer as the answer key? 24.1429. 14286. Not so different. There you go. Here, I already applied distributive property. Perhaps I should have done that to make the solution a little cleaner. But I think that's just vanity at this point. At least we got the answer. Number 5. 27 grams of water absorbs 1,500 calories of heat energy. The temperature was raised to. Note that preposition to. So this is definitely final temperature. And yes, we could already say that it is actually what we're given is the final temperature, because what we're supposed to look for is the initial temperature. We're still talking about water, so the specific heat is 1. This is actually, it actually is better to distribute it, to modify the equation before we substitute the values. C is 1. Okay. What is 27 times 57.5 minus 1 5? 27. Basically, we have 1.94. And this is temperature, so degrees Celsius is the unit. 1.94. Is that the answer? Yes, sir. Okay. We won't be answering number 6. This is definitely out of my league. I don't think we even answered this in school. Maybe we did, but I don't remember exactly. But it was definitely one of the last questions. If ever we did answer it in class, it was one of the last. So it didn't really count at that point. Usually the first and the medium questions are part of the pointers, but definitely not the last ones. Usually. Okay. I think this is 1. Okay. Let me add a page. I did answer it, but let's answer it again. So this is a kind of problem that is going to need you to memorize a lot of formulas. So here we have to calculate the total thermal energy that is required in order to evaporate 100 grams of ice from a temperature of negative 3 degrees Celsius to 104 degrees Celsius. So, oh frick, what is this? Not again. Anyways, where do we start? Okay. So I think we have 5 steps here. The first step is from solid to melting point. So we'll label our energy as Q1. Basically, in the end, we have something called Q total. You find the sum of all of the Q's that will be computing. I think for this scenario, we have 5. Do we? Yeah, 5 Q's. Specific heat of, right now, we have a solid ice. So what's the specific heat of solid ice? It's 0.5. What's the change in temperature? From the initial temperature, that is negative 3 degrees Celsius. Well, that's initial, so should be here. What's our TF? So the melting point. Melting point is 0 degrees Celsius. Everything good so far? 100 times 0.5. Correct. So what's the answer? 150 calories. Number 2. This is from melting point to liquid. So technically, we still have the same mass, 100 grams. What is the specific heat of... I guess it's already a liquid now, is it? What's number 2? Oh, wait. Okay, made a mistake. Please, sorry about this. So this is where we find the relevance of MLF and MLV from earlier. So right now in number 2, we are melting ice at 0 degrees Celsius. So Q2 is not MCAT, it is MLF. Let me actually illustrate the graph right now as we're speaking. So in this part, the substances, or basically the water, is solid. It's in ice form. Here, it's in liquid form. And anything above is vapor form. In this region, from solid to liquid, liquid to solid, is the latent heat of fusion. Between liquid and vapor, we have the latent heat of vaporization. As for water, like what I said earlier, the melting point is 0 degrees Celsius. The boiling point is 100 degrees Celsius. So where are we right now? In number 1, looking for Q1, we were here. For Q2, we are here at the LF level. I hope that's clear. Okay, so LF is a constant. It's 80 calories over grams without the degrees Celsius. That's the difference of LF and LV units with ordinary units. Well, particularly the unit of specific heat, supposedly, as you can see here. LF, the unit is cal over G only. There is no degrees times degrees Celsius at the denominator. So 100 times 80. Mass is still 100. So if ever you forget that this is actually the formula, like what happened earlier, I noticed something different, something wrong. What specific heat value am I going to use? Is it in the solid form or the liquid form? Well, it's neither. You cannot use a specific heat value because it is in this part, melting or freezing point. That also goes the same for if you're in the evaporation point or boiling point. Okay, so 100 times 80, that is what? 8,000? Is it? 8,000 calories. Yeah, so it sure does take a lot of energy to get the ice through its melting point. Unlike this, it only takes 150 calories. Here, it's a significant amount of energy. Okay, let's move to 3. Ouch. Anyways, so this is from liquid to gas form. So Q3 is equal to MCAT. Q3 is equal to the mass, which is 100 grams. The specific heat of water is 1. What is the change in temperature? The final temperature is the boiling point, that is 100 degrees Celsius, minus the initial temperature, that is what? 0, I guess. The melting point. We just came from the melting point. Let's see if we're right. Yes, we are. Okay. So 100 times 100, that's 10,000. What's the unit for energy? That's calories. Okay. How about Q4? We just to let you know, so far, this is Q3. Q4 is going to be in the level of LV, or the latent heat of vaporization. So, boiling water at 100 degrees Celsius. Q4 is equal to, instead of MLF, the F becomes V. Okay? Q4 is equal to the mass, 100 grams, times the LV, that is 540. Where did where do you know that it's 540? It's here. Where do you get 80? It's here. LF of water. LV of water is 540. Okay. 540 what? What's the unit again? Calories over grams. So cancel the gram unit. We have calories as the unit for the final answer. 54000. 54,000 calories. That's a lot. And finally, number 5. Vapor form onwards. Usually we stop here if the final temperature is only up to 100 degrees Celsius, but we still have extra 4 degrees, so we still have to add another Q, that is Q5. So from there, we already have an idea that the initial temperature is 100 degrees Celsius. We just came from the boiling point. The final temperature is supposed to be 104 degrees Celsius. Q5 is equal to the mass. What is the mass? 100. Specific heat, that is, well, right now we're in vapor form, so 0.48, or basically 0.5. Let's just stick with 0.48. Calories over grams times degrees Celsius. Okay. So what is the answer? 200 calories approximately. Well, yeah, let's just place 0.5. It is 400, right? Do I remember it right? Sorry, 200. Okay, so now, at this point, we have already found the 5 Qs. Now this is where we're going to use this one. So Qt, or Q total, is equal to 150 cal plus 8,000 cal plus 10,000 cal plus 54,000 cal plus 200 cal. So what's the total? It appears to be 72,350. Okay, demonstration is complete. One of the most satisfying things in physics, literally. Okay, let's move on. Do we still have time? It's getting pretty late, actually. I'll make a part 2, but for now, at least, I was able to cover Ohm's law, thermal expansion, and calorimetry. Like I said, um, everything here is important. The 80, the 540, for the LF and LV respectively, as well as the specific heat values, you have to know them. Um, Linear coefficient values as well, and the thermal expansion equations, especially this change in length. I think this one is a change in area, although I don't think we touched that much in class, as well as the change in the volume, because there's a beta. We didn't have that. As well as this, LF is equal to LO plus delta L. Did I discuss thermal expansion enough? I don't, doesn't feel right. You know what? Let's actually discuss it. Like, again. This time with proper context. So, an unknown object has a length of 30 meters at night. So this is nighttime. With a temperature of 24 degrees Celsius. So we have the final length that is 30. I knew it. It was supposed to be 30.125, not 3.125. Something's. I knew it. Well, I think it's time to make things right. TF is 35 degrees Celsius. We're looking for the linear expansion, that is the A. The calligraphy A. Change in L is equal to LO watt. And then LF is equal to LO plus change in length. Okay? Change in L, well, let's use that later. Let's do this first. Use this later, use this first. So, do something like that. LF minus LO, that is 0.125 meters. A is equal to delta L over LO delta T. LO is 30. TF minus TI, 35 minus 24, that's 11. Times 11. What is the answer? 330. Okay, 0.00038787. Just say 88 over degrees Celsius. By the way, I almost forgot to mention, Um, what is the unit of linear expansion? It's over degrees Celsius. Yeah, I think I did mention it indirectly. Like in a fixed value, this is the unit, over degrees Celsius. This doesn't look nice. 1, 2, 3, 4, 4. Oops. 3.78 times 10 raised to 1, 2, 3, 4. If we're moving to the right, that's a negative, I guess. Yeah, I believe so. So yes, that's the answer. Well, we got the same answer anyways. What? Wow. Yeah, I only copied it wrong here, but technically, the change in L was still 0.125. The entire solution is still correct technically. Okay. Number 2. What is the length of the steel rod at 20 degrees Celsius? TF is supposed to be 20 degrees Celsius. Observed to be, so TI, 30 degrees Celsius. LO is 50 meters. LF is missing. We're talking about a steel rod. So what is the linear coefficient of a steel rod? I actually forgot. Wow. Anyways, what is it? Steel is 12 times 10 raised to negative 6. I think 23 is aluminum. Okay. So, what is the formula? Okay, LF is missing. Okay. But we're given the linear coefficient, so I guess we'll use this formula first, then that one. So, yeah, we have to look for the change in L. Steel rod is 12 times 10 raised to negative 6 over degrees Celsius. LO is 50 meters. Delta T, or change in temperature, is TF minus TI, 20 minus 30. But then here, ideally it's supposed to be T high minus T low. Let's actually use this one. I believe what sir said, what my teacher said. So 30 degrees minus 20 degrees. 500. Okay. Calculator is pretty useless at this point. let me get an actual calculator. Bear with me. Twelve times 10 raised to negative 6 times 500. 6 times 10 raised to negative 3. These cancel. What we have left is meters. That's impossible. A change in length cannot be negative, right? I mean, wait. It is technically a positive integer though, but it's just very, very small. It's definitely less than 1, but still greater than 0. Ah, yeah. I think we are in the right track. What I did here was Tf minus Ti, not T high minus T low. Either way, this cannot be a negative variable. It wouldn't make sense. I think we are in the right track. What's our LO? 50, right? Plus 6 times 10 raised to negative 3 meters. LF is supposed to be 50.006. I think there is something wrong with our answer. Because we came from a higher temperature. Our temperature right now, the final temperature is lower. So supposedly, logically, the object is supposed to not expand. But based on our answer, it appears that it did expand. So I guess I don't know what to believe anymore at this point. I guess my teacher is wrong in this part. It's supposed to be Tf minus Ti. Negative 10, right? So this is supposed to be negative. This is supposed to be minus. So in that case, if it's a minus instead, the answer isn't that. It's this. 49.994 meters. Which is exactly the answer in the answer key. Okay, it's quite... I mean, it's supposed to be easy. Maybe it's because it's been a while since I've studied these. Like, I remember the exam was back in May 21, May 20. Somewhere during that time. It's been like almost 2 months. I mean, more than 2 months already. Anyways, I'll see you soon for the next video. That will be about frequency period waves, mirror equation, index of refraction, Snell's law problem, and perhaps we could also touch concave, convex, plane mirrors, lenses, those things. They're technically part of physics, grade 12. Initially introduced in grade 9. Okay, that's it for this video. Thanks for watching.